you can see my screen?
Mm-hmm.
Yeah.
All right. Yeah, welcome to the fourth EMEA Online Meetup. And this time, Shirin is presenting on trust and prediction of machine learning models, which I think is a really interesting topic and a very important topic, especially in times where machine learning is getting more and more really into production. And you have a lot of cases where you have to convince people of using it. And this can be a very important tool to help you doing that. So I never really looked deeply into that. And I'm really looking forward to hear about that from Shirin. Okay, so this is how it goes. Like every time, we'll have a little community discussion about recent topics, and then Shirin is going to present. We have 45 minutes for the presentation and Q&A. Usually I would say that we'll take questions during the presentations. Probably not do that excessively because it's interrupting Shirin, but if there's something which you need to know in order to understand what's going on, then you can, of course, ask this question. And also you can post questions in the Zoom chat. I will have a look at those questions and forward them to Shirin. And yeah, so next month, Christian, a well-known member of the TWiML community, is going to present on deep learning for remote sensing or analyzing satellite images. And yeah, that's interesting too. Whoa, what was that? You should probably mute yourself. Okay. Last time we had someone starting to brush his teeth in the middle of the meetup, including video and audio. Okay, so if you want to present a paper yourself, please reach out to me on Slack, LinkedIn, or via email. Yeah, and again, probably most of you will know that, but we are hosting a lot of study groups, especially for the Fast.ai courses, deep learning and machine learning. I think deep learning, the new or the course running at the moment, is coming to an end in, I think, 2 sessions. And Christian, how far is the ML course? Do you know that?
I think we have like 2 or 3 more sessions to go.
Yeah, so this round is almost over. I don't know, did someone already say when the next deep learning Fast.ai course is going to start, the version 2, where he's showing how he created this library?
I think end of March. I think there were dates for the live scheduling in San Francisco, and I think they were like 20th or 22nd of March. Okay.
So I'm really looking forward to that one. That's going to be an interesting thing, seeing how this how the Fast.ai library is created. Yeah, okay, so I just told you how we handle the questions. No need to tell that again. Okay, so community discussion. Is there something you want to discuss or a topic you want to hear about? Unmute yourself, jump in if you want to talk about something. Did someone watch the interview from Jeremy with Leslie Smith? I think I wasn't able to watch the whole interview. I just watched the beginning.
Yeah, I did, but the audio was really bad. So
yeah, unfortunately. Yeah, but it's worth watching, you would say. Yeah,
if you have good speakers, can
okay.
Kind of home in what's happening. So it's a bit hard to follow, but it was I think a good one.
Hard to follow because of the audio.
Yeah.
Okay. Yeah. Okay. And so if someone of you attended on the last meetup, we talked about tools and stuff. And we talked about the NVIDIA Docker images. And I just saw today that they released the new PyTorch images, Docker images. And actually, I just a few minutes ago checked them, and they now have PyTorch 1.0 on board. So it's definitely now natively possible to build an image with PyTorch and Fast.ai. I'll do that hopefully in the next few days. And yeah, that's pretty good. Okay. Anything else?
Maybe from the Slack forums. Since the courses, Fast.ai courses are reaching an end, we're discussing what to do in the meantime. And there's various ideas about doing Kaggle competitions or just kind of a coordinated learning thing till March, till version 2 goes live of the Fast.ai stuff. So it's not yet decided what we will focus on. There's a kind of a list and some voting going on what to do. So if anyone is eager to jump in and join, it should be just in the Slack Fast.ai channels, and you can just take part and move it in the direction you want to go.
Yeah, that's a good thing. So there is the option to meet up weekly or bi-weekly, I think, right?
Yeah.
Okay.
And also on the which Kaggle competitions or old competitions to tackle and what to do, basically.
Yeah.
Where the interests are. Yeah.
Interesting. Okay. All right. Someone is asking where you can find the video. When you Google Jeremy Howard, Leslie Smith, then you will definitely find the YouTube video of the interview. Yeah,
I think it's also linked in the Fast.ai forums, but I'm not sure if it's in the restricted area or in the general one.
Yeah. Okay. So if no one has another topic to talk about, we can start with the main presentation. And I would hand over my screen to Shirin.
Yeah, you have to quit first.
Oh yeah, okay. Yes, did it.
Okay. Can you see my screen?
Yes.
Perfect. Yes, all right. As Kai already said, I'm going to talk about trust and predictions of machine learning models, and I'm specifically going to present the paper Anchors by Marco Ribera, and I will talk a little bit more about it, of course, what it is. But yeah, this is the first page of the paper. Not very exciting, but you see it's written by Marco Ribeiro, Samir Singh, and Carlos Gestrin from the University of Washington and California, Irvine. And they've been working on the explainability and interpretability of black box models, or model-agnostic methods, for quite a while. And the first time I got to know about this was from a TWiML AI podcast, actually, where they had, I think, it was Carlos Gestrin as a guest, and he talked about the LIME paper. And I found this very interesting, the idea that you have a method that enables you to at least get an approximation of your machine learning models that you otherwise just have to basically trust in based on performance metrics and your, I'd say, trust that you did a good job building these models. So, and as I said, LIME is the first model-agnostic local explanation algorithm that they developed, and it has been developed in 2016, but there are some drawbacks, and I will talk about them later. So what they actually published this year is this Anchors paper, which is the next iteration of trying to explain black box models. And you find the link below. There is the PDF of the paper. Yeah, but before I start, just a few short words about myself. So yeah, I'm from Germany, from Münster, and I studied biology originally. I did bachelor's, master's, PhD, as you do in biology and research. And I also spent 2 years as a postdoc, mainly working with next generation sequencing data. So I was a bioinformatics postdoc. But I also started blogging during that time, and I got really interested in machine learning particularly. So I tried out different machine learning tasks, machine learning projects, ideas, what other people did. And I wrote a blog about this. And over time, I got more and more interested in this part of data science and data visualization and statistics. So I decided to become a data scientist and leave academia. So now I've been almost 1.5 years at the company. I'm currently working for CodeCentric, and I work there as a data scientist doing all kinds of projects from fraud detection to predictive maintenance and natural language processing, all kinds of things. So yeah, before I explain Lime and then of course anchors, I thought I would give a broad introduction to why is explainability and interpretability actually something that is interesting and something that we might want to think about when we build machine learning models. So the typical machine learning workflow usually looks something like this. We have data collection. We usually need to clean our data and prepare it, normalize it, transform whatever we have to do. Then comes the model training part. And usually we choose the best model from a collection of different algorithms, hyperparameters, whatever we tried out. And we define a performance metric, and we say one of these models is the best model based on this performance metric that we chose. And this is usually where it ends. And if we are data scientists, we are often very confident in these performance metrics and these numbers like accuracy or kappa values, we have precision, recall, whatever you have. But often these, or sometimes at least, these can be very misleading. So we can have high accuracy, probably all experience this. A high accuracy doesn't necessarily mean that your model is actually good, that it's actually doing what we think it is doing. And there can be actually many cases where models, especially image classification models, they learn something from the background because the data was somehow biased and we didn't notice this before. And what is actually learned is not a generalizable representation of the data, but something that is specific to our training set. And we just didn't notice because the accuracy was still good in our training set. So we always have to ask ourselves, can we really trust the model that we just built, and is it really fit for the wild? Because you can imagine a model that does not perform as we expect will usually fail at some point and will lead to more or less severe consequences. So there are many reasons I want to argue why we should improve our understanding of machine learning models. And I want to give you at least 3 of the major ones here to, I hope, convince you, if you are not already convinced, that it is worth spending the extra time and effort to gain a better understanding of our machine learning models, even if it's technically not necessary. So the first reason is to improve our models. So of course we can train our model based on performance metrics, whatever, and they are ready to ship, they are ready to deploy. But I want to argue that if we understand our models better, we can actually improve them and have a sort of sanity check. So we can be extra confident that our model actually learned what it's supposed to learn and that there are no wrong conclusions or maybe biases in the data that we didn't detect before. So we can have an extra layer of making sure that our model performs as expected, and we can thus prevent wrong conclusions. And I say there are potentially at some point adversarial attacks, but this is something that's not possible right now, but it's something that's very interesting. I mean, adversarial attacks, for those who don't know what they are these how do I describe it? When you have an image and you have an image classification model, there are some ways how you can manipulate the pixel values so that you don't notice anything strange with this picture, but your machine learning model will completely fail. Was there a question? No, okay. So maybe at some point we can actually find a way to detect adversarial attacks. The second reason that doesn't have anything to do with us and with our model just from a deployment and improving our model standpoint is the morality and ethics standpoint, so trust and transparency. Of course, if we cannot understand our machine learning models, we won't be able to say if these decisions are trustworthy, if they are based on specific features, so we are not able to explain to a bigger public or to decision makers or whatever why certain decisions have been made. And what goes hand in hand with this is if we don't understand how it's happening, how it's making decisions, we of course won't know if it's fair or if there's some bias that's either created or reinforced. And this is particularly important if we think about models that directly affect people's lives. Let's say this model that's, I think, in use in California, where they have a model that helps judges decide if a prisoner is going to, was supposed to get parole or not, if he's of a high risk to come back to jail later in his life or her life. So it's really difficult to know whether these models that you build are actually making fair decisions, or if they are based on societal biases that are obviously in the data. I mean, any type of data that works with people's information will have the bias that we have in our society there, be it race or gender or whatever. So how can we find explanations without sacrificing complexity and accuracy is a big question. Because we do usually have the case that the simple models that we can explain, like linear models, they are not good enough to really model complex behavior or complex patterns in data. And the really complex models, like neural networks, they are able to find really complex patterns and do really difficult tasks, but they are also so complex that we have no chance of really understanding what's going on. So there are many, many approaches, and this is something that people have been thinking about for quite a while, and I just name the most, I say, common, the most popular approaches that are out there. So LIME is of course one, and anchors, but there is also something called partial dependence and ice plots, also Ale plots. Then we have Shapley values, we have tree surrogates, we have a nice package called breakdown, and these are the ones that I see most often. So here I just want to briefly give you an idea what all these other methods are and why LIME and anchors is different. So partial dependence and ice plots are basically a way to graphically visualize the marginal effect of, let's say, one, or usually you only have one or two variables, and you see how they are, what the effect is of this variable on the outcome. So here, this example is from the wine data set, where I built a classification model and I predicted the wine quality. And here you can see the two outcomes, qual high and qual low, so quality high and quality low. And you see the feature alcohol, and you see the pattern, the partial dependence here, that tells us high alcohol tends to be more strongly associated with high quality than low alcohol. And if we have, so the partial dependence plot would be the yellow line, but if we plot this for every data point, we get these black lines, and we call this individual conditional expectation plots. So they are similar to the coefficients in linear or logistic regression models. But as I said, we usually only show this for one or at least two variables, because usually more than two variables will, again, create such complicated effect interactions that we are, again, not able to really understand them. And this applies similar to Ale plots. I'm not going to go into detail what they are, but if you're interested in this kind, Ale plot is basically a different way to calculate this marginal effect. And then we have Shapley values. Shapley values are also often used, and they are actually, I would say, after LIME and anchors, the most promising method. because it applies methods from game theory. So it will basically calculate how much each player, so each feature, contributes to the end result, so the classification that is made. So we get weighted contributions for our entire feature set, and we can compare it to the actual predictions. So here you see, again, the same alcohol data set. This time we have the Shapley values for different features and the values that these features have. So we can see that sulfates of 0.56 is associated with a low quality.
Do those values sum up to 1 for one feature?
I don't think so, but I'm not entirely sure. Maybe they do, actually.
Okay,
yeah,
so
I'm not sure.
Is that comparable to feature importance for tree methods?
Not.
Okay, so that, I think I understand. So it's showing the contribution for a particular prediction, right?
Yeah, exactly.
Okay,
so,
interesting. Yeah.
Usually what these traditional, let's call them traditional methods have in common, they usually do something where they fix certain features and then they change some minor things for a feature and they see how is the effect on the outcome. So if I change something in an important feature, of course the outcome will change drastically. If I change something with a feature that is not important, nothing will change.
Yeah.
So the basic idea.
Yeah.
So here, the interesting thing with Shapley values is that they are based on probability distributions of predictions. So that this makes them interesting because you can actually, get the distribution, the information of the predictions of a bigger set. But all these models are not perfect, obviously, and LIME has some very interesting techniques to improve this approximation of the explanation, basically. And LIME is called Local Interpretable Model-Agnostic Explanation, and the name already describes the main parts. So local means it will find local explanations for instances at a time. Interpretable, of course, the explanations that come out should be interpretable by us humans, so it should be easy to understand what they mean. Model agnostic means they can be used for any type of classification model in this case. And yeah, they give explanations. So the original paper of LIME was Why Should I Trust You? Explaining the predictions of any classifier by the same 3 guys who published the Anchors paper. And it has been written in Python, but there is an adaptation for R. It's not completely the same package, but it is similar. So the implementation is similar. It is different in a few minor things, but the idea and how it works is basically the same. So how do these local model-agnostic explanations work? So the first and very important thing is that they only capture local explanations. So you will only get explanations for one feature at a time. And so the rules or the feature importances that you get out for each instance, they are only valid for this one instance. So they cannot be generalized to global rules that apply to similar cases. They are really just valid for this one instance. So then explanations are given for this one instance at a time, as I said. And in LIME and Anchors, explanations are given on original features. And this is important because when we think, for example, of deep neural nets, what will happen is, of course, that the deep neural net will calculate complex abstractions of the original input features, and the explanation in the end, the classification in the end will be based on these abstractions of the original features, but not on the original features themselves. But since we are not able to understand all these explanations, all these abstractions, LIME and Anchors both aim to go back to the original features so that we have a chance to really understand them. So how does LIME work? LIME takes a machine learning model, so any machine learning model, because it's model agnostic, and it will take the instance or sample that we want to have the explanation for. And now the first thing it will do is we'll create a permutation or perturbation set of this one instance. And I will explain this a bit more in a minute. Just to give you the rough overview here, I'm going to go quickly over this. This permuted data set, so this collection of instances that are sampled from the original instance and changed a little bit, we will use to make predictions on with the original machine learning model. So we will get a collection of predictions, and we will have the distance and similarity of every of these permuted or perturbed samples in the set. So we will know how much was changed from the original instance to each of the perturbed samples, and how did this affect the prediction, basically. Then we will use different methods to calculate the most important variables. So we usually say have up to 10 important variables where you want to have explanations for, because otherwise it will get too complex again and you won't be able to understand it. And now we use this and build the local model. So we basically fit a local model and use as weights the similarity metrics that we calculated before. And with these weights that come out of the model, we get approximated explanations. So here's everything a bit more in detail. So sampling happens from a distribution curve or kernel density function. Or if we think about, or we have a text classification model by randomly leaving out words. And yeah, so basically we will get the collection of similar instances based on one original instance. And we make the predictions on every perturbed data set, data instance from this with the original complex machine learning model. Then we calculate the distance measure for each perturbed data point with the original instance. And we convert this to a similarity metric. And the defaults, this is for the LIME-R package, are cosine similarity for text models, Gower for tabular data, and Euclidean distance is also something that's often used. But you can basically use any type of distance and similarity measure that you like. Next, the most important variables that are chosen, there are different ways to choose them. You can, for example, choose them with forward selection and rich regression fit. You can use highest weights and rich regression. You can use lasso regularization or decision tree splits. And now the interesting part, the local model that is now fit to these similarity metrics and the predictions that are calculated. So we will fit this model locally, and the output that is used is the probability of each possible class that can be predicted. So in LIME, at least in the R package LIME, rich regression is the default simple model that is fit locally. But again, in principle, any model that you can interpret can be used. So here I have 3 examples how the output of LIME looks like. So and this is now for a tabular data model. So just a very simple table where we have patients, and for each patient we have different features like hemoglobin values and different lab values, and what we predict is whether they have chronic kidney disease or not. And the output that LIME will produce in such a case is this bar plot, and we see on the x-axis the weights, and on the y-axis we see the features, and these are the most important features that were calculated. And you see what value the feature had for this certain instance. So here, case 4 is the first instance where you want to have an explanation for. And for this case, it was predicted to be CKD, so chronic kidney disease, with a probability of 98%. And now we see all the green bars. They show us features that contributed to this prediction. So let's say here, the hemoglobin value between 0.38 and 0.46 very strongly contributed or supports the prediction chronic kidney disease. But what you also will find is that these, so hemoglobin here is in all 3 cases the same, but just because hemoglobin of this value supports this prediction in one case, because the instance has its own explanation that's independent from all other explanations in all other instances. We don't necessarily find the same rule for all cases. So hemoglobin values between these two borders, they don't always support the prediction CKD. For image models, this looks a little bit different because here we work with superpixels, and superpixels are these clusters of similar pixels that you see on the left. And what Lime basically does, it randomly removes these superpixels and then makes the predictions. And this way you will get pixels that most strongly contributed to a prediction. For example, the first one, the first row, we have the prediction banana, and in the middle, this is the VGG16 model prediction. It predicts this to be a banana with 99% accuracy. And the blue pixels here, the blue superpixels, are actually the pixels that Lime says contributed most strongly to this prediction. And on the right is my own model, and here you see something similar, just a different way to plot this, where you see the superpixels that most strongly contribute to this. The same we get for text models. Here we find words that either support or contradict a certain classification. So now the pitfalls of Lime. Because Lime uses linearly weighted combinations of features, it very much depends on how good the fit of this linearity actually applies. And if linearity doesn't really apply, the explanation doesn't make any sense and can't be trusted. And also the coverage is not very clear because these instances have their own very unique set of explanations. It's not easy to say when an explanation can be generalized and when not. And this makes them not extremely intuitive to understand. So here is where Lime actually is much better. And Lime works with rules in this case. So it doesn't have these weights. It will actually calculate rules that you can very easily understand. And the way this works is, again, we start with an instance. For example, here, the text classification model from the paper. This movie is not bad is one review. And what it does now is has a model again that makes predictions. For example, it predicts this to be a positive review. And now there will be rules. And rules can, for example, be the presence of certain words. Here in this case, one rule can be if the words not and bad are there, then the rule equals 1. And what happens now is, again, we get a conditional distribution for similar reviews. So if we take our instance and we perturb it again, similar to how Lime does it, we get a collection of similar reviews. And we can now look if this rule applies, what happens to the prediction. So we can now see whether we have so-called anchors, and anchors are called rules that occur basically with high probability. So if, for example, our rule, if the words not and bad occur, then the prediction is positive review. If this has a high probability of being the case in our conditional distribution, then we say this is an anchor. So here a bit more detail about this. The perturbation distribution is abbreviated E in the paper, and as they quoted from the paper, they must use interpretable representations, so they have to make sense for humans. And in the case of this LSTM text classification model, as I just said, words were randomly replaced. So this is how they changed these samples, and they changed these words randomly, but with words that have the same past text. So if there was a verb, it will be replaced with a verb. If it was a noun, it will be replaced with a noun. And then we have these if-then rules, abbreviated A, so a set of predicates. And as I just said, for example, we can have the rule, it contains the words not and bad. And our anchors, if the rule is a sufficient condition and if it occurs with a high probability. And the paper uses the threshold 95% for an anchor. So here's an example from the paper on structured prediction. And here they have, again, past tags for the word play. And they have several instances, so sentences where the word play occurs. And the model is now supposed to predict if it's a verb, noun. Yeah, a verb or a noun. And anchors, in this case, would be the neighboring words or the previous word. So these are the rules. If the previous word is particle, prediction play is verb. If the previous word is determiner, prediction play is noun. And if this rule occurs with a high probability, this is called an anchor. There is a similar example from the paper on tabular data. On 3 different data sets, you can actually find the examples in a GitHub repository. And here, it's again similar perturbation by fixing the features for some rules and sampling from the rest of the row. And now here we get more or less complex if-then rule combinations. So for example, if no capital gain or loss and a person was never married, they are predicted to have an income of less than 50,000, probably dollars. And here you can also see that these rules are not true in reverse. So just if the rule is if no capital gain or loss and never married, it predicts less than 50,000. This does not automatically mean that the reverse is true. So everything that is not or that is capital gain and was married does not automatically mean they will be predicted to earn more than 50,000. We can again apply the same thing also to image data. Here is a little bit different because if the superpixel is present or absent, and how they perturb the images is this time they will replace pixels with random pixels from other images instead of setting them to 0 as line does. So the advantages of anchors over line are very clear. So the coverage is obvious. You can always know if an anchor applies because these if-then rules are so easy and so intuitive to understand. And of course, anchors can also capture nonlinear behavior. So they do not depend on this local goodness of fit for linearity. But of course, also anchors has limitations. One of them is that these anchors or these rules can be very complex and very specific, particularly for cases near the boundary. So there can be very complex interactions of many, many features. So these if-then rules become very big and very complex. And of course, anchors can give conflicting patterns, even though they say in the paper this is not very common. And if it occurs, it's maybe a hint that something is wrong with your model. But another limitation is that explanations are usually only given for one class, but it would be better to give explanations for every possible class. But again, this will make things even more complicated and even more difficult to really understand. And the thing that I find maybe most difficult to wrap your head around is that many explanations can exist in parallel, because these explanations are only valid locally again for every instance separately. You can have explanations that exist in parallel and that may be different for different instances. And of course, the distribution of the perturbed samples that has to reflect reality, and the perturbation has to be interpretable. So with this, I want to leave you with a take-home message and have a discussion, because that's actually the interesting part, I think, to really discuss this paper and the ideas and see if it applies to you and to your work. But I really like this quote from the paper that really sums up what anchors are and how they work. Is in contrast to line, even though they use the same distribution D, anchors are by construction faithful, adapting their coverage to the model's behavior. All right, with this I want to thank you. I also have the links in my slides, which I will share. And yeah, let's discuss.
Okay, first thanks a lot. And so if someone has a question, I definitely have some. Please just unmute yourself and ask the question. Or write it in the Zoom chat down. Okay, so one thing that came into my mind when I saw the Lime thing, for example, is how is it in terms of computation? How efficient is it to do it for each of the instances you have?
So I have to say I did not have time to try out Anchor. I only worked with Lime so far, and Lime isn't very fast. So Lime does take a few seconds, up to 30 seconds, I would say, to calculate the explanation. So it's not something that you can do in real time with streaming data, for example. Okay, so for each instance you want to check, you have to compute all this and okay. Mm-hmm.
Interesting. And is it a problem when you use, or is there something like, can there be something like overfitting? Can you use the data that you trained the model with to check the explanations, or would that be not correct to do that?
I think that would not be correct to do, but it's in general very difficult to assess how good or how trustworthy the explanation is. I mean, Lime gives you these explanation fits, and if the explanation fit is not close to 1, it's definitely not trustworthy, but even so, it's relatively difficult to really be sure that these explanations are valid enough, let's say.
Yeah. And is this computational efficiency that so that it takes pretty long, is that because of the implementation, or is it not possible to make it faster? Can you, for example, do it in parallel or something?
I have to say I'm not an expert on this type, so I'm not really sure what's going on. So I was asking the guy, Thomas Peterson, who implemented Lime for R, whether he also thinks about implementing anchors for R, and he said it's not possible because it would simply take too long.
Oh, okay.
But since I'm not an expert in this, I'm not sure why that is and if that can be changed somehow.
Is it taking too long to implement it, or too long to
run? That it's
run?
not feasible for people to use this because it takes.
My understanding is it has to run the model many times on sort of slightly different versions of data, so that's a limitation.
Yeah, sure, but it's probably parallelizable, right? I mean, you can, okay.
Yeah, I don't know. Maybe nobody has the most efficient implementation yet. I don't know.
Okay, and what I would find interesting is, did you ever encounter? So, did you use that in customer contact in the wild out there, and did it improve your projects when you have the ability to, kind of explain that? Because that's actually something that I encountered not just one time, that it's very hard to convince people, especially people that are not in this world of machine learning and don't know much about it, to use a neural net for something, and you can't even explain how a decision is made by such a black box model. And did you actually encounter something like that, or?
So yeah, I have been using this with projects I've been working on for customers, mainly honestly to have the double sanity check for myself. And the customers I had so far were luckily relatively positive about machine learning, and they had an implicit trust, I have to say. So I never really had to convince someone that they have to trust my model in this sense, but they still liked these explanations. So they still like the idea of having a way to understand what is going on in the background, particularly if they if they are maybe interested in finding new patterns that they hadn't seen before. In the fraud detection case, for example, they were interested to maybe find new strategies of fraud that they didn't know before. I mean, they didn't end up finding any, but this was an idea where potentially Lime could have helped them find new rules or new techniques that they didn't know, new patterns in their data.
But that did not work.
It did work, but they didn't find anything new. It was all known, basically.
All known. Okay.
Yeah.
Yeah, very interesting. And I actually did not completely or fully understand how the anchors for the tabular data work. It makes kind of makes sense for the text data, but can you maybe elaborate a little bit more on that? How it's how the anchors for tabular,
So yeah, here they take the data again and they fix certain parts of the features and randomly change the rest by sampling from the distribution again. So it's very similar to how Lime does this, as I understand.
Okay.
So that's what you wanted to know, or more?
Yeah, and what's the anchor part then and
the rules that you have here are so the example they have here are mainly if you see no capital gain or loss are a factor categorical feature. And never married as well. Then we have work hours, which is a numerical feature. So here we have thresholds where the rule may say if work hours is bigger than 45, the prediction is, in this case, more than 50,000 income.
Okay, yeah.
So rules.
Yes, okay. Any further questions? Don't be shy, unmute yourself and jump in.
I was wondering, how is that different, like these bootstrapping approaches? I only saw them once, I think, for linear regressions. This, what's it called in R? Rela Info or something? Relative importance. And I think they use bootstrapping in some way. I'm just wondering if that's...
These are feature importance methods, right? Feature importance measures. Feature importance usually is measured on a global scale. So you will get feature importance for a global method. But because for different instances, this doesn't really apply. And it's very difficult to really map down to individual instances and explain the behavior of your model for all these different cases. That's where anchors and Lime are actually different because they have these local explanations there.
Okay.
But some of the ideas are similar. Yeah.
Okay.
I was wondering how the generated anchors are different than decision trees.
That's a good question, actually. Yeah. You're right. This would be very amenable to having decision trees make these anchors.
Is it that you're not generating these anchors to cover the whole data set like you would with a decision tree? It's kind of only one or two examples at a time? Or?
But I'm not sure if you could achieve something similar with decision trees on a local basis.
I was a bit reminded of the waterfall charts as well from the ML course, Fast.ai, that you have these kind of contributions. Yeah. Interesting.
I mean, decision trees.
Sort of like how you come about generating these rules is completely different, I guess. But
yeah. I mean, it's not trying to differentiate the data by any algorithm. It's knowledge from someone putting this in, right?
But you could maybe derive these rules with decision trees and then check whether their probability is high or not, and then model them anchors. I mean, there are tree-based methods to explain machine learning models, and they work with decision trees. So I don't know if we can combine this.
But for a global scale, it's like feature importance from gradient boosted trees or something. Yeah, but that's actually the interesting point of this kind of algorithms. So I mean, I think feature importance is one of the things that everyone is knowing when he's doing machine learning stuff. But this is really trying to explain a single instance or a single prediction. That's pretty interesting for cases like you just told me, if you are should get parole or not, and if you do such kind of systems, then those kind of local interpretability is really important. And also, if those methods are, they will surely be advanced, and in medical applications, for example. I mean, this is not interesting when you put out advertising, I think, but when you do it for such kind of applications, and to my mind also, I would immediately think of decisions for machines, for example, if you should shut down a machine for maintenance and that kind of stuff. So that are decisions where a lot more is involved in than, yeah, I don't know, in advertising or something. And so that kind of models are really interesting for that applications.
Yeah, and also if we think about GDPR, I mean, it's very interesting to know whether these types of explanations would actually fulfill this criteria that you have to give explanation, or that you have to explain the behavior of algorithms that make decisions that affect people's lives.
Oh, yeah, that's really interesting. Do you know if that's feasible? Is it possible to use something like that to?
I'm not sure if this would be like if a judge would say this is a sufficient explanation. Yeah. But it could be very interesting too.
I'm sure that in some time a judge is going to judge about that. So maybe you have to go there and explain him how this works.
Yeah.
Yeah, that's very interesting. I really did not think about that, but yeah, and actually for GDPR you need to explain if you use such kind of models.
Yeah, you have to say when you use these models and how they basically work. So how they make decisions. And with this, yeah, so as I said, I'm not a lawyer or anything, but it sounds as if you are not really allowed to use black box models in this case anymore.
Yeah. Yeah, well, I'm pretty sure that this is there is no decision out there that says that you can use that kind of explanation or not. That's definitely something that at some point a judge is going to tell maybe the highest judge, and then we'll know if that's possible. But that's interesting. I did not see it from that side.
Yeah, and another thing that's very interesting to think about is what do we do if we detect bias? For example, if we see on the left here this RCDV recidivism for Doan's example, where we see that for parole, that the prediction for rearrested is associated with the rule that it's a male and he's black and is not married. So the male and black part. So what do you do if you detect this in your model? Will you take these features out, even though they have maybe very strong prediction importance for your prediction, or how can you really deal with bias that you detect in your models?
Yeah. But you would also find that when you use feature importance methods, right? So you would also find that male and black is for high importance.
Probably, yeah.
Yeah, very interesting. So actually, I don't know if everybody knows what GDPR is. What we just talked about. It's I don't know. Do you know the exact?
General Data Protection Regulation of the EU.
Yeah, and one of the rules that is very much talked about, especially in the ML community, is that in the future, if you make any decisions that have to do with people that are based on machine learning models, you have to be able to explain how this decision took place. So you have to basically explain the model, and that kind of means that for certain types of decisions, you are not allowed to use black box models like neural networks. And it's going to be interesting to see if that kind of algorithms that can explain such things for local instances can help there. But I'm sure that this is something that is going to be decided in the courts. So.
Is that something European, GDPR?
Yeah, yes. The new EU data protection regulation. It has been in effect since May of this year.
Yeah, it's actually very important for American companies too, because a lot of the Facebook, Google, and all of those. I think it's the second biggest market for them in the EU. And so that's going to affect them too.
It's like any company dealing with data on EU citizens or something.
Yeah.
Does GDPR really rule out neural networks? I mean, and didn't we see that paper where the guy published, I forget what his name was, he published a paper showing that there's, you can actually see what the layers of the network are doing in terms of image processing, looking for edges and looking for finer features. That's an explanatory, so that in that case they've explained what the neural network is doing. It's not a black box.
So you mean the paper by Zeiler and Fergus, right?
Yeah.
I mean, CNNs are special because there you can actually visualize what happens and you can understand it from a human perspective, because of course we see all these activation maps and we see what features or what patterns are recognized, and we fill it with meaning because we, of course, humans say, this is a cat ear and this is a pattern it's recognizing, right? So this is a little bit different than other, I'd say, normal machine learning tasks. Yeah,
and also I'm pretty sure that GDPR does not rule out neural networks. There's nothing about neural networks in the GDPR, but there is the rule that you have to be able to explain how a decision took place. Mm-hmm. And that without that kind of algorithms that help to explain how the decision took place, it's not possible to use it, because for a neural network, you don't naturally see what's happening inside.
Yeah, it's a bit vague, this GDPR.
Yeah.
But,
I think because it's a fairly new legislation, it's not clear exactly how the courts will interpret that explanation requirement.
Yes, there's going to be a lot to decide in the courts, and hopefully none of us is going to experience that decision.
And pay a lawyer rather than listening to people in the ML meetup.
Well, it sounds like a progressive regulation, though, when we've had cases like this recidivism one, where there is clearly bias in the decision making.
Yeah,
we do need to be able to detect it and deal with it.
Mm-hmm. Yeah, definitely.
Yeah, I mean, that cases like this parole or no parole decision helping, that's really hard. And when it's really true that there is like male and black, one of the most important features, then
that's problematic.
That's hard.
Yeah, probably because the majority of cases in the US are already biased towards male black people. The same if you have models that match job applicants to different job positions, and you have a history where, let's say, the majority of nurses were females and the majority of software engineers were men. So of course the bias is in our data, so machine learning algorithms will pick up on these rules.
Yeah, absolutely.
That's what I said before. I also don't really have a good answer for how would I treat my data to prevent something like this from happening.
Yeah, you have to remove certain features.
Yeah, but even if you remove them, there are often so many hidden correlations in the data that even if you remove them, you can't really remove the effect.
I think it was a TWiML podcast a few weeks ago. It might have been another podcast where it was like, sometimes removing them isn't the right thing to do because there's like positive effects in combinations with other variables that you're now getting rid of.
Yeah, that's going to be a very interesting future for the topic for the future, for sure.
It is.
Yeah. Okay, so we are on top of the hour. Shirin, thanks a lot for this presentation and insights. Very interesting.
Yeah,
and also the discussion about bias in data.
Yeah, I really like the discussion part. So I'm very interested in getting others' input on these things.
Yeah. All right. So again, this meetup is going to be on YouTube. I will post it on Slack, and I think it's going to take a few days until it's uploaded. And yeah, thanks a lot. Have a great Christmas time, and see you next year.
And the slides, are we going to post the slides?
I will post them on my blog. Just my name, Shirin-Glander.de, and I think Kai can also post the link probably, right?
Yes, I will post it on Slack.
That'd be great.
I'll
Thanks.
probably upload them tomorrow.
Okay. Thanks very much.
Thank you.
Yes, thank you, everyone. Bye.
Bye.
Bye-bye.
Bye.